We are talking about the independent samples t-test, and we talking about this variance sum rule and all this craziness with how to estimate sigma. So, knowing this sort of variance sum rule, we talked through a bunch of this stuff up here. The variance of the sum or difference of two independent samples is equal to the sum of their variances. This is true whether you're adding two variables together, subtracting them. The result is the resulting variance is going to be sort of adding the two variances together, and which all by itself isn't super useful, at least for right now. We're not really thinking about sort of adding or subtracting stuff, right? In terms of our goals here. We're not taking two variables and adding them together or whatever, but what we are doing is we're going to be subtracting the means of two variables. So because the standard error, so this is really talking about variance, right? So if we take variances of anything, right, sigmas, if I want the variance, say, of x1 minus x2, well, it's going to equal to the variance of x1 plus the variance of x2, assuming that x1 and x2 are independent. And since we're doing an independent samples t-test, it sort of works, right? We are assuming that they're independent. So if we know that these two things are independent, we can just add their variances together. If we want to subtract them, or if we want to add them, it doesn't make a difference. If we want the variance of this new variable, that is the addition or subtraction of these two things, then we can just simply add their variances together. It makes it kind of simple. We don't even have to do the process of adding and subtracting. We can just deal with their variances and figure out what that would look like. Well, again, we don't want variances, we want standard errors, right? We're interested in not a variance, but we want the standard errors of the mean, right? Standard errors of the mean, like when we did a one sample t-test, right? We wanted the standard error of the mean, so we can take our t-test is equal to, like, our mean for x minus the mu over that standard error of the mean, if this were a z-test, right? Because z's actually had the sigma in there. So if I want to do a z-test, it would be like that, where the t was just a mild transition, a little shift, where the top looked the same, but we just substituted our sample standard deviation in, and we got a standard error of the mean based on our s. So in the same way, we gotta think about this. In order to figure out what we can do with the sample standard deviation here, we first need to think about, well, all right, well, what do we know, what we can do if we had the actual sigmas, the population. So for a second, let's think about, okay, if we knew the population, what could we do? What could we assume? All right, so say for a second, we knew the population variance, or population standard deviation, or if we were pulling things from two different populations, we knew both of those sigmas from those populations. If that were true, we could figure out what the standard error would look like, the standard error, the difference between two means. We could figure that out if, knowing the variance sum law, we converted the standard errors into variances. Because remember, a standard error is like a standard deviation, but for samples, for means of samples. So with that being true, we could square those standard errors and make them into variances. So I know that, okay, if I add those two variances together, I could get a variance version of the difference between the two means, right? The squared version of it. Well, we know that the standard errors are simply the standard deviations divided by the square root of n. All right, so we know that. That's down here. The standard deviation, right, for x, for instance, just the standard deviation over the square root of n. Well, like I said, in the earlier part of this, if I want to turn this into a variance, I need to square it. All right, so if I square the whole thing, what that does is it gives me the variance on top over, and it just gets rid of the square root over n. So I get these variance versions of standard errors by simply squaring everything, and I get the variance over n. So that's why you see the variance of one x over n, the variance of the other x over n, and these are two different variables. I can simply get the variance versions of the standard errors by squaring the standard error equation, and I get the variance of x1 over the n for x1 plus the variance for x2 over the n for x2. These will actually give me the variance, the squared variance versions of standard errors. All right, so because I know I can add two variances together, right? I can add two independent variances together to give me the resulting subtracted or added variance. I could simply add those two together, and this is going to give me the variance version of the standard error of the difference between two means. All right, that's great. But I don't want the variance version. I want a standard error version. I want it without the square. So to get get it without the square, well, anything that's squared, like a variance, if I want to get rid of the square, all I have to do is just take the square root. So if I take the square root of the addition of those two variance versions of standard error, right? I can add those together, take the square root, and I'll get the standard error, the difference between two means. And again, you can think of this like the Pythagorean theorem, like Pythagoras, right? If I know one side of a triangle and the other side of a triangle, this is A and this is B, and I want to figure out what C is, I can't just take A plus B equals C. I have to square A, square B to get a C squared. And then if I want C, I have to take the square root of C squared to get it back to C. So to find the C, I have to square A, square B to get C squared, and then take the square root. That's what I'm doing here. I'm taking the A squared plus B squared, right, equals C squared. And then to get C by itself, I got to take the square root of it to get it back to its original form. And if we do this, we can actually figure out the standard error, the difference between two means. And what we're trying to figure out here, just to remind ourselves of the bigger picture, what we're trying to figure out here is if I take a bunch of samples and I subtract them from each other as I pull them out of a population, and going back to this picture over here, all right, if I take a bunch of samples, take two samples at a time, either two populations or the same population, and I subtract them, I'm going to get a difference. I'm going to put them back. I'm going to take two samples out again and get a difference. I'm going to put them back. Take another two samples out, get a difference. I'm going to keep doing this over and over again, and I'm going to create this distribution here that should capture in the middle whatever the averages of all those sample differences are going to be. It should average out to whatever the differences between those two populations are. And if you think the populations are equal, this will often be 0, because if the populations are the same, or if it's from the same, taking samples from the same population, you'd assume that they're not going to be different on average. So this oftentimes will be 0. But it's going to capture whatever the real differences between those populations are by simply taking all those samples out. And I can figure out what the standard error is, how much these are going to vary. I can figure that out using that equation that we just figured out, right? I can take the variance version of the standard error, the squared standard error, these two things. I can do it for the two different samples. I can add them together, take the square root, and that would tell me how much I expect the two samples to differ from each other on average, and how much they would vary. Sometimes sample 1 is going to be larger, sometimes sample 2 is going to be larger. So I'm going to get a variety of negatives and positives, and it's going to give me a nice sort of normal distribution, assuming that these sort of n's are large enough. Okay, the n's are in the 20s or something like that. All right. So let's move on. So if these are coming from a population where sigma is known, then we can plug this in and we can figure that out, right? And we can actually do something akin to a z-test by saying, okay, the difference between my two means, right? The two means of the samples I have, because I'm doing one, like in our case, one of them's playing Grand Theft Auto, the other one's playing that Lego game. And I want to know if there's a real difference here. Well, I went and figured out what do the differences look like if I just were to let them, just be, right? Let them vary on their own. I could figure out what that would look like, and that would give me the means here, the two different populations. I can figure that out. And again, oftentimes this will be 0, so you're going to see that this will oftentimes sort of go away. It'll assume that this is, it doesn't have to be 0, but probably 9 times out of 10, this is going to be 0 because we're assuming that the populations are not different from each other. The only difference that occurs is because of what we do to them. Right? If I pull people from a population, randomly pull them from a population, I'm assuming that the differences are going to be, they're going to be roughly the same, and that on average that there's going to be 0 difference between them. And that's why it says here, if you can see the little arrow here, it says this represents the null. Now, again, the null doesn't have to be 0. It could be a different number, but again, most of the time it's going to be 0. So if we assume this is 0, this sort of simplifies out some. But the main thing here is that I want to look at the difference between my two means, and I want to have this standard error that represents that distribution of the difference between two means at the bottom. So I could figure that out. I can actually do a z-test if I know the population values. I can figure this standard error, the difference between the two means. I can figure that out using this equation, and I can plug that in and get a z-test. Right, but here's the problem. What if we don't know the sigmas? And we typically don't. By typically, I mean hardly ever. I mean, it's not going to be, the idea of knowing the population standard deviations is really slim to none. So this is sort of just a step to figure out, okay, well, what could we do? So if we knew the sigmas, we could do a z-test. We're not going to know them. It's very unlikely. So if you don't know them, we're going to have to figure out a way to use S, our sample standard deviation. In this case, because we have 2, our sample standard deviations of the 2 samples, we're going to have to plug those in somehow. We're going to have to use this to fill in for this somehow and do a t-test instead, which again, 99.99% of the time is what's going to happen. You're not going to know sigma. You're going to have to figure out a way to do this. So because we have 2 samples, we're going to have to take 2 different steps. There's going to be 2 steps to actually get to an S version of this. So again, going back a second, this is, if we knew sigma, right, we could do this. We could plug sigma in for the 2 of these, the population values, we could plug them in and figure out a standard error of the difference between the 2 means. When we don't know it, we're going to have to use S somehow. And again, to use S is going to take us a couple steps. We can use our S's, our standard deviation of our samples, to estimate this sigma sub, mx1 minus mx2, this difference of the standard error of the difference between the 2 means. I can use this if, and down here it says, if the variances of the samples are roughly equal. This is something called the homogeneity of variance assumption, and if we pool the variances together. So the logic here is that if I have some kind of population, wherever this is, let's say we're using just a single population, and I get a couple different samples out of here, and I get a sample here, and I get a sample there. And whatever, I did some stuff to them to make them different. Each of these are going to have their own standard deviations. All right, so if I just want one standard error, but I have 2 different standard deviations, each of which are going to be, an estimate of our population. I'm going to be able to estimate the population using either one of those. So because I have 2, I need to figure out a way to sort of incorporate both of them in. So if I can show that S1 is sort of roughly equal to S2, right, which is that the homogeneity of variance assumption, actually really in squared form, if I can show that the variances are roughly equal, then what I can do is I can pool them together. So pooled variance is another way of saying sort of averaged variance, but the reason why they don't use average is because it's a weighted average instead of just a simple average. So a simple average, really just you add up stuff and you divide by the number of things you added up. That's a simple average. A weighted average is a little bit different. And what it does, it says, well, if one sample, let's say this sample had an n of 10, this sample had an n of 100. Well, I know just from experience and from things I've been taught and everything that a sample that has more people in it is going to have a better estimate. So this S2 is going to be a better estimate of the population because it's based on a larger sample size. This one's going to be, you know, a much worse estimate of the population because it has a smaller sample size, but I still don't want to necessarily ignore it. So I got to figure out a way to use both standard deviations, but to allow this one to contribute more to the estimate. So we're going to weight this more because it has more people. We're going to weight this one less because it has less people. And we're going to average the two variances together to get a pooled variance. And then we're going to use that pooled variance to estimate. So we're going to use this, some kind of pooled variance estimate, to estimate our population variance. We're going to estimate our sigma squared using a pooled estimate of these as long as they're roughly equal. So that's what the two steps are. If we think or can prove that the variances are roughly equal, they're homogeneous, right? Then we can pool them together, but we're going to use their sample sizes in our favor. We're going to take advantage of the fact that they may be of different sample sizes, and we're going to pool them together in a smart way in which we sort of weight the different samples depending on their size. All right, so we assume the variances are equal. So the reason why we have this sort of homogeneity or equality of variance assumption is because if they're from the same population, if we're pulling two different samples from the same population, then they both should be estimating the same population standard deviation or population variance, so they should be equal. And it's sort of the idea that if I have a population variance and I have a variance from sample 1 and a variance from sample 2, well, if this is estimating this, right, and this is estimating this, they're both sort of the estimates of the same population value. Using the arrows here, right? They're both estimating the same thing. Well, then they should be roughly equal. Right? Because if they're both trying to estimate the same population value, then they should be roughly equal to each other. All right, well, what about if they're two samples from two different populations? Well, even if they're from different populations, we need to be able to compare them. And to be able to compare them, they got to be on the same scale, have roughly the same amount of variability, or else when we compare their means, if their means don't mean the same thing, if they don't represent the same numbers numerically, if they don't represent the same scale, then we probably shouldn't be comparing them in the first place. So if one scale is much more homogeneous and has a smaller amount of variability, well, that variance is representing a variance. That mean is representing a different sort of set, a different scale of numbers, and one that has a much larger variance. So the idea is we're assuming that the variances should be roughly equal so that the means are comparable. Because if both the means and the variances are changing across the two groups, then we really can't compare them. It's like saying, I mean, it's not quite this exact, this drastic. It's like saying, well, I measured one group using American dollars, and I used another group measuring, I don't know, English pounds or something. And to be able to compare the average amount, well, those averages don't even mean the same thing because they're representing different scales. So if the variances are drastically different, that gives us a clue that maybe the scales aren't the same and the means aren't representing the same information, so comparing them really probably isn't appropriate. So the reason why we're assuming, again, is that if they're from the same population, they should be equal anyway. But if from different populations, we want them to be roughly the same so that it makes sense to compare their means. Okay? That sort of, you know, comparing apples to oranges analogy people like to use. So if one sample, like when we did our one sample t-test, we said that one sample is the only sample we have. So we're going to take our standard deviation, our S, and we're going to estimate our population value with it because that's all we have. That was the best estimate we had. All right. But what if we have two samples, then taking the average or something of the two sample variances is going to be an even better estimate of the population, right? Because we know that, you know, as samples come out of a population, we know as we pull them, sometimes they're going to be, it could be a little bit wider, a little bit skinnier, just by the nature of sort of, pulling things out. So each one of these is a good estimate of the population, but if I average them out, I'm probably going to get closer. I'm going to get closer to the real value of the population by simply averaging them. And if I had 3, it says 3 or 4. If I had 3 samples, then averaging all 3 of them would be even better. If I had 4, averaging all 4 would be even better. The more samples we have, the more information we have from the samples, the better we can actually estimate the population. Now, with that being said, though, however, if one sample is larger, then we should pay attention to that a little bit more. Right? A larger sample is going to give us a better estimate of the population value, so we can't really ignore that. So that's when there's this idea of sort of a weighted versus a simple average, or a simple average is what we're used to. If I want to take a simple average of variances, I can take like the variance of sample 1 plus the variance of sample 2, and I can just divide it by 2. That would give me a simple average. Where a weighted average is a little bit different. I need to actually use the n somehow to weight this one. And usually what we're going to use, we're going to weight it by the degrees of freedom. We're going to take our n for 1 minus 1, and I'm going to multiply that by its variance. I'm going to take the n for 2 minus 1, and I'm going to multiply it by its variance. And then I'm going to divide by a common degrees of freedom, which is going to be n1 plus n2 minus 2. The reason why I'm subtracting 2 here is because I have n minus 1 there, n1 minus 1, I have n2 minus 1 there. So n1 minus 1, if I were to try to add those degrees of freedom together, right, what I get n1 plus n2, and I'm subtracting 2 out, which is what this is. Right? All I'm doing is recombine the fact I have n1 minus 1, n2 minus 1, just reconfiguring into, well, n1 plus n2 gives me my total n, and I'm subtracting 2 degrees of freedom because I lost 1 there and I lost 1 there. All right, so we'll talk more about this in a second, but the idea is I want to be able to weight them. I want to be able to take the weights, take the sample size into account when actually pulling the variances together. So this theoretically is a better estimate of sigma. So if I'm able to take a pooled variance, right, some kind of weighted average of the sample variances, this is going to be the best estimate of our population variance. So by pooling or averaging out our sample variances here and weighting them by size, I can get this pooled estimate. This is going to be our best estimate of our population variance. Then we can actually then use this as a replacement for this in our equations. All right, so so I just sort of, wrote that out, but let's think about how we can pull them together, what that actually means. So if you remember that, a variance, a single variance, we've defined that as the sort of the sum of squares over degrees of freedom. Remembering the sum of squares is that sum of xi minus mx squared. It's the sum of square deviations that we sort of shorten and just call the sum of squares. All right, so we have the sum of squares and over degrees of freedom. Degrees of freedom typically is the number of people in the sample minus 1. So knowing that the sum of squares, that any variance is the sum of squares over degrees of freedom, we can use that information to sort of pull things together. So if I want to pull them together, I need to pull the sums of squares and I need to pull the degrees of freedom. So the pooled variance is, if we pool the sum of squares and degrees of freedom, we can get it. So if I want a sum of squared pooled and a degrees of freedom pooled, I would simply just add together the sum of squares from the 2 different samples, then add together the 2 degrees of freedom from the 2 different samples, and that would give me a pooled variance. All right, so we can think, all right, sum of squares for 1 over its n1 minus 1, that's my 1 variance for sample 1. And I can do the same thing with sum of squares for 2, and I can then divide that by its degrees of freedom. Or I can reconfigure it. If this is n1 minus 1 plus n2 minus 1, I'm going to get rearranged n1 plus n2 minus 2, and this is going to be the typical sort of degrees of freedom you're going to see for a t-test. All right, we're losing 2 degrees of freedom because we have 2 samples and 2 sample means. So we're going to lose those 2 degrees of freedom there. So I'm going to add our 2 ends together, subtract 2 for the fact we have 2 means and 2 different samples. So I'm going to add together my sums of squares. I'm going to divide by this common degrees of freedom, and that's going to give me my pooled S squared P, or S squared pooled estimate of our, it's the best estimate of our population we can get by simply sort of pooling the 2 samples together. So we can get the sum of squares in a couple different ways. I can either actually, if I want to add the 2 sum of squares together, I gotta calculate the sum of squares. I can either do that by going through the process of subtracting everything. So the sum of each score in x1 minus the mean of x1. Do that for all the scores, squaring them as I go, add them all up, and get the sum of squares for 1. Do the same thing for sample 2, and do that. I can do that. But if I'm given the variance, like if I'm supplied with the variance for group 1 and group 2 as part of a problem or as part of a exam question or practice problem or something like that, if I'm given the variance, or the standard deviation for that matter, if I'm provided with the information, I can simply just convert my variance back. I can take my variance, I can multiply it by its degrees of freedom, and that's going to convert it back to a sum of square. So remember, sum of square divided by degrees of freedom equals variance. So if I take variance times the degrees of freedom, I'll turn it back into a sum of square. So that's all I'm doing here, is saying, all right, I want my variance for x1, I'm going to multiply it by the n for x1, or the degrees of freedom for n1, for x1, and that's going to convert it back to a sum of squares for x1. I can take my variance for x2, multiply by its degrees of freedom, and I can convert it back to a sum of squares for x2. This is much easier than trying to go through and do all of this each time you want to get a sum of square. So I can just take my degrees of freedom and work my way back to a sum of square, so that when I combine it together, by the way, one thing I should mention too here is if the n's are equal, right, if the n for sample 1 and the n for sample 2 are equal, you can bypass a lot of this, because when you go to weight them, because the weights are the same, the weights don't really matter. So if the n's are equal, I can just pool variances by simply adding the 2 variances together and dividing by 2, because we don't need the weighted. So the weights don't matter because they're the same weight. Right? There's no point in weighting the 2 different samples, right? Because the weights are equal, we can just sort of add them together, divide by 2. That's easy. When the n's are unequal, have 2 different n's, then we need to do this process to convert this one back to its sum of squares using its degrees of freedom, convert this one back to its sum of squares using its degrees of freedom. So again, this is the sum of squares for 1, this is the sum of squares for 2, just converting them back to sum of squares, adding those sum of squares together, dividing by this common degree of freedom on the bottom, and that'll convert it to a pooled variance where the 2 different groups are weighted. The larger group gets to contribute more to the average, where the smaller group contributes less to the average, right? So it allows for the larger, sort of better estimate of the population to be able to contribute more to the average, which makes it closer, better, should make it a better estimate of the population in the first place. Once we have the pooled variance estimate, so we've done that, found the S squared pooled, I'm now going to replace sigma squared, the population variance, I'm going to replace that value with the pooled variance in that original equation. Go back a second. Let's go back a few slides. Remember when we found the standard error based on sigma, we had sigma squared for x1, sigma squared for x2. We divided by their n's. We simply added them together, took the square root to get a sigma sub m1 minus m2. This is our standard error based on the population values. Well, since I don't know sigma, I've gone through this process now of finding the best estimate for sigma, which is our pooled variance, our S squared P. So now that I've found the best estimate for my population variance, well, I can go back and now replace it. So I'm going to put the S squared P, that pooled variance, in place of my population value. So divided by the n for sample 1. This one divided by the n for sample 2. Notice it's the same number, because we're assuming the variances are the same thing, right? We're estimating the same population, so the pooled variance should apply for both. And I'm going to divide. And notice that if the n's are equal, again, I can take this S squared pool divided by n1. I can just multiply it by 2 or add it by its, to itself. Take the square root of that, and I'm going to get a sample version of the standard error, the difference between two means, based on S, but using the pooled variance estimate as our best estimate of sigma. Once we have that, I can plug it in here, and that converts this over to a t instead of a z. All right, so we're using the sample estimated version, plugging that in here. This is still going to be my based on my null hypothesis, which often will be 0. So a lot of places you'll see this sort of drop out. So I'm going to take the difference between my two sample means minus whatever the null hypothesis states, which usually is going to be 0, over the standard error, the difference between two means. That's going to give me a t value, and I can look up a t critical value in a t table and compare my t to t critical and see if these two means are significantly different. All right, so to sort of rehash that, to get to this t, we need to estimate a sample-based standard error of the difference between two means. To do that, there are two steps. The first step is calculate the pooled variance. All right, we're gonna average the variances of the two samples together to get our best estimate of sigma, or sigma squared. Once we have that, I can plug the pooled variance in for this standard error equation, right? Add them together, take the square root, and I get my standard error, the difference between two means. Once I have that, my third step in sort of step 6, right, and calculate the test statistic, is to plug that number in here and figure out my t. So here's the data again, just to sort of review. We have the Grand Theft Auto game. We have the Lego City Undercover. Grand Theft Auto, there's 8 people there because 2 dropped out. And we have the Lego, there's 10 of them. We know that the mean for Grand Theft Auto is higher than the mean for Lego. They have, they're 2 different innovations, 2 different variances, but look, they're really, really close together. We can now compare these 2 different samples to each other, knowing what we know, knowing that we can pool these variances together and then estimate a standard error that way. We're set to go. We can now actually go through and actually calculate this. So let's talk about step 1. Step 1 of the 7 steps of hypothesis testing. So I can do this as a 2-tailed or a 1-tailed test, depending on how I plan to go about it. A 2-tailed test is always sort of non-directional. It's where you say like, oh, I really don't know what to expect about the differences, so I'm just going to say I think they're going to be different, but I don't know how. This would be something like the null would be, well, okay, if I subtract the 2 means, like Grand Theft Auto minus the Lego game, I would expect them to equal to 0, right? No difference between the 2 of them. So our type of game has no impact on aggressive behavior. That's the sort of null hypothesis. For the alternative hypothesis, it's the same thing. I'm going to take my GTA minus my minus my Lego, so GTA minus Lego, and I'm going to assume I'm testing whether or not that is different than 0. So for a 2-tailed test, all I'm really saying is I think the type of video game will have an impact on aggressive behavior, but I don't know which way it's going to go. Now you might believe this, you might be testing this because if we know that there are 2 competing theories or hypotheses about how a violent video game might affect behavior. Again, I think I mentioned in the last lecture or so that you may think, all right, so aggressive behavior will make people more aggressive, but you might think that aggressive video games may be sort of cathartic and maybe give people a release of their aggression, a release of their sort of violent behaviors or whatever, so that afterwards they may be less violent. They may actually help to relieve some of those tendencies. So if you are unsure of which way it might go, you might do a 2-tailed test because you think, well, I think there's going to be a difference. I just don't know which way it's going to go. for this particular example, it seemed like a one-tailed test is likely to be more appropriate, where because I think the Grand Theft Auto is going to lead to an increase in aggression, and that's what I want to test here. My alternative is that I think my GTA minus my Lego, right, the difference here is going to be greater than 0. So when I'm looking at the number of aggressive behaviors, that there's going to be more aggressive behaviors after GTA than there is after Lego. So I expect that difference to be positive, greater than 0. So another way of saying this sort of verbally is Grand Theft Auto leads to more aggressive behaviors than Lego City. The null then is just going to be the opposite with an equal sign. So if I think that GTA minus Lego is going to be greater than 0, the opposite of that is, well, GTA minus Lego is going to be less than 0. But also if it's equal to 0, meaning there's no difference, that also is going to go against my hypothesis, right? So this is going to be less than or equal to 0. So here I think GTA leads to the same or less aggressive behaviors as Lego City, which is my null hypothesis here. All right, so again, you wouldn't do both of these. You would have to decide, do I want to test this as a two-tailed test or as a one-tailed test? And that would depend on, you know, what your beliefs are, what the hypothesis you're trying to test is, and how much you know about the variables in the example. And oftentimes, if you're thinking, well, I don't care about any of that. All I want to know is, how do I read, you know, a word problem and decide? So look for key words. Two-tailed tests will say something like, you'll see words like different, or not the same, or is there a change? So you'll see that you hear these sort of very ambiguous terms about how the groups might be different from one another. So if you're reading through a word problem and it says the researcher is interested if aggression is affected differently by Grand Theft Auto or Lego City Undercover or whatever. So the fact that differently doesn't give you really any direction. It just says, I think they're different, but without saying which one's which. For one-tailed tests, look for directional things like, I think this is better, it'll increase, decrease, you know, look for those directional terms. Does Grand Theft Auto lead to an increase in aggressive behaviors or something like that? So if you look for those terms, it'll sort of give you a clue of what the example, what the word problem is trying to lead you towards in terms of a two-tailed or one-tailed test. So here we need to decide on the steps 3 and 4 really are, all right, well, what kind of test are we doing? And, you know, what are we assuming about our alpha level, our type 1 error? So if you notice in the original setup, we weren't given sigma for either group. We don't know anything about the population. We're not given those values. So we cannot perform any kind of z-test. There's no independent sample z-test that can be performed because those sigmas aren't there. So we have to estimate sigma, which gives us a clue that it's going to be a t. Because the groups are independent, and we know they're independent because they were selected from the same population and then randomly assigned. So that two-step process tells you they're independent. And so what we're doing here is an independent samples t-test. Unless it says otherwise, which you might see some practice problems, it'll say something like assume alpha is 0.01, or it'll give you a different number. But if it doesn't say anything, this is one of the places where it's safe to assume that alpha is set at 0.05 or 5%. So if you see nothing about, or a statement about alpha in a word problem or example or something like that, that's the one time it's sort of safe to assume that it is going to be 0.05 unless otherwise stated. So for step 5, we need to figure out the critical value and the decision rule. Okay, so the critical value is going to come from a t table, which I think is on the next page. Yeah, it's going to come from a t distribution, and we need the degrees of freedom for it. All right, so we know the degrees of freedom. As we said before, we have one sample that's n minus 1, so we have their degrees of freedom. And we have the degrees of freedom for the other sample, which is n2 minus 1. So I can either add those two together. All right, so this would be, there's 8 people in group 1, so that's 8 minus 1 is 7. Group 2 has 10 subjects, 10 minus 1 is 9. So I can take 7 plus 9 is 16. Or I can say 8 plus 10 is 18, minus 2 is 16. Now, either way, you're going to get to the same number. Okay, so I can either add up the two different degrees of freedom to get 16, or I can just add up the two n's, subtract the two ones that we have, the one there and the one there, and then I'll get us to the same number, 16 as well. Okay, so the important thing here is that when you are doing an independent samples test, it's the only one of the t-tests and things we talked about so far. A one sample t-test is just the degrees of freedom are n minus 1. A dependent samples t-test, because we're subtracting and getting just one set, it is also n minus 1. For the independent samples t-test, because we have two different groups, we have to add the n's together and subtract 2. Okay, so we're losing 2 degrees of freedom because there are two means that are being estimated, so we're losing 1 per group. If I had 3 groups, I'd lose 3. 4 groups, I'd lose 4. And we'll see that when we come back to analysis of variance, as we have more groups, we're going to lose 1 degree of freedom per group. So I'm going to add up all my n to get one overall capital N, and then I'm going to lose 1 degree of freedom per group. In this case, I have 2 groups, so I'm losing 2 degrees of freedom. So just for the sake of completeness, I'm going to go through what the one-tailed value would look like and what the two-tailed value would look like, but you wouldn't do both. That's why it says or here. If you had decided on a one-tailed hypothesis in step 1 and 2, then you would continue doing a one-tailed here. If you decided on a two-tailed test at step 1 and 2, then you would continue to do a two-tailed test here. You would not do both of these, but let's just talk about both of them for the sake of completeness and talking about everything. So looking at the one-tailed, I know I have 16 degrees of freedom, so I need to look up a one-tailed t-test at 0.05, right, with 16 degrees of freedom. So I just happen to have that on the next page, just for convenience. So look up here, one-tailed, 0.05. All I have to do is just follow this column down until I get to 16 degrees of freedom, which is here, 1.746. 16 degrees of freedom, 1.746 is my one-tailed value. So let's go back a page. 1.746, then goes here. 1.746. So my decision rule, if I'm doing a one-tailed test, is that if my t observed that I get from my test is larger than 1.746, I'm going to reject the null hypothesis with this one-tailed test. Okay. But what about two-tailed? If I did it as a two-tailed test, all that does is sort of shift it over a column. So instead of looking at one-tailed here at 0.5, I'm going to go to two-tailed here at 0.5. I want to start, I'm looking here now at 0.05. I'm going to follow that down to 16 degrees of freedom to this 2.12 number. So as a two-tailed test, this is going to be 2.12. Right, so that's my critical value. And really it's plus or minus 2.12, right? Because it's a two-tailed test, which means it can go in either direction. So I'm going to have a 2.12 here, but I'm also going to have a negative 2.12 here. So if my critical value is either larger than 2.12 or lower, less than negative 2.12, either way, I'm going to reject. So one way to think about that is if, because it's two-tailed, if my absolute value of my t observed, right, absolute value is greater than 2.12, I'm going to reject the null using a two-tailed test. All right. Just for the sake of, again, completeness and stuff, let's look at the actual t table that you have on Canvas. So this table is sort of a truncated small version. It only goes to 25 or whatever, and the values look a little different. Let's look at what it might look like if we went to the full t table and just sort of check to see if we're getting similar results. So let's go to here. I think I have the tables down here somewhere. Okay, so if I go down to my t table here, again, it looks the same. It's just a lot bigger. There's a lot more numbers, right? So if I look here, it's the same thing. If I'm doing a one-tailed test here, I'm going to start with this column 0.05 for one tail. And then I'm going to scroll down this column until I get to my required degrees of freedom, which is 1.7459. So in the other table it was 1.746 because this was just rounded up, but 1.7459 would be the critical value looking it up on the full T table. Right? So we're getting the same information, similar at least. And then if I'm doing it as a two-tailed test, right, so two-tailed is the second sort of set down here. I'm going to go to 0.05, which means I'm just going to shift over one column to the right. I'm going to go down to 16 degrees of freedom here, which is 2.1199, which on the other table is 2.12. You see it got rounded up. So 2.1199 is our critical value, and it's the same as if we did it this way. But just to give you some experience looking at this table, those are the two different places you would start and scroll down to here. So those numbers could be put there. They're the same numbers, just one goes to 4 decimals, the other one goes to 3, but they look very similar to the numbers you find in this table. This is just I had shrunk this down some and made it a little bit smaller just so it would fit on a slide and be able to be readable, and have it be a little self-contained. But those numbers are reflected in the larger table. It's just these only go to 3 decimals, the other one went to 4. They're the same numbers. All right, so step 6 now is where the sort of the meat is, where most of the sort of work gets done when you're going through the 7 hypothesis testing steps. Right, step 6 is where you actually compute the test. So we have means of 10.25 and 8.4. All right, so it looks like there's a difference in the mean aggression between the two groups, but we need to test them. So it's not between the sample and the population mean. It's not between, it's not two dependent samples we can subtract. So we need to do this as an independent samples test. And for that means we got to go through these sort of sub-steps of step 6. So the main thing is what I want, the end result is going to be that I want my 2 different means for my samples here. And I'm going to compare that to my population mean differences here, and I'm going to divide by standard error. This is my goal for step 6. This is the test that I'm trying to compute. Under the null hypothesis, all right, let's go back. When we stated our null hypothesis, we said, if there's a difference between aggressive behaviors, let's look at the one-tailed test. So if Grand Theft Auto has more aggression than Lego, when I subtract them, I expect that to be different than 0. So notice it's centering around this idea of 0, where the null says, well, if there's no difference between the two of them, that would equal 0. And if for some reason the people playing Lego become more aggressive, it's going to go in the opposite direction. I'm going to get negative numbers. But it centers around this idea where null has an equal to 0 value here. So if playing Grand Theft Auto or playing Lego really has no effect on people's aggression, well, I would expect them to look the same. I expect them to get the same aggressive behaviors. And we subtract their means, it should be 0. Right? So that's why stating here, based on the null hypothesis, I expect this to be 0. So under the null, mu1 minus mu2 is 0. Again, if there's no difference between the two groups, I expect 0 difference, no difference between the two of them. So oftentimes, again, this drops out, and what we get is that I want the difference between the two means over the standard error of the difference between the two means, and to do that, we'd actually get our t observed. But as we said before, there's a couple steps to get here. So step 6 actually has a couple sub-steps we got to get to first. So we need to calculate that standard error of the difference between the two means. And to do that, we first need to calculate the pooled variance. So this is the equation, right? We get n1 minus 1 times the variance of group 1, n2 minus 1 times the variance of group 2, and then n1 plus n2 minus 2 on the bottom for degrees of freedom. So we got to do a little tracking some stuff down in our example. I don't think I have it on the next page. No, I don't. So I know that in my first group, because 2 people dropped out, this is 8. So 8 minus 1, and this is for the GTA group, right? And this one is for the Lego group. Okay. So I got 8 there. Here I have 10. So I know that's my degrees of freedom. 7 for this group, 9 for that group. But what I need are the variances. So I got to go back a second. So the variance 2.786, I'm going to guess it's somewhere close to here. 2.786. And the variance for the other one's 2.713. So I'm assuming that's probably here somewhere, 10 minus 1, maybe 2.713 is the variance for the Lego group. And those are my two variances. Now notice that it says, you know, variance 2 and it's squared here. But the variances, because this is a variance, these two are already squared. I don't need to square them. If I instead had grabbed the standard deviations, let's go back a second. You know, if I was looking at the data here, and I instead grabbed the standard deviations, let's say the variances weren't available, they weren't given to you, all you have were the standard deviations, then I would bring those two numbers over and I would square them. I would square them to turn them into variances. Because the variances are already given to us, I don't have to do that. They're already squared. So don't put the variances in and then square them, because you're looking at the equation and you see the square there and you think, oh, I need to square this. It's referring to the variance, which is already squared, so you don't need to square it again. All right, so this is the variance of group 1, variance of group 2. And then on the bottom, I'm just going to plug in the same numbers again. This is now going to be 8 plus 10 minus 2. Okay, so let's do this piece by piece. So 8 minus 1 is 7. 7 times 2.786 equals 19.502. So I can put that number here. 19.502 is the weighted variance for group 1. And if I do 9 times 2.713, 9 times 2.713, I get 24.417, which goes here. 24.417 is my weighted variance for group 2, my Lego group. And then 8 plus 10 is 18, minus 2 is 16, which we already sort of had figured out before, but just to remind ourselves, 16. So now all I need to do is add those two together, divide by 16. So 19.502 plus 24.417 equals 49. Actually, I'll even write it here just to be complete. This is 49.919 over 16. Okay, so 49.919 divided by 16 equals 2.7449, so 2.745. And this is our pooled variance. So this is the sort of step 1. I'm going to pool the variances together. Now you may be thinking to yourself, one of the things we said earlier, that I said earlier, was we should pool them together if they're homogeneous. And I haven't even talked about homogeneity at all. If you look at the two of these, 2.786 and 2.713, they're super, super close together. So I didn't even bother to look at it, you know, are they or are they not homogeneous? They're homogeneous. I mean, they're almost identical. What starts to happen is sometimes when they aren't exactly identical, so this one might be 5.786 and this one's 2.713, and you're asking, well, are those two the same? There is a test for it that I'll just mention here because it's worth this idea of looking at homogeneity. All right? How do we look for homogeneity? When you're looking at it, when you're running something in, say, SPSS, you're going to get a test. It's like Levine's test of homogeneity of variance that comes with your t-test, right? So there is something called Levine's test that you'll find in SPSS, right? And that's covered sort of in the labs. And you want Levine's test to not be significant. Significance here tells you that the variances are significantly different, right? So that's one way. So one way is through Levine's test. But this isn't super handy if you're doing this by hand. So on an exam or something like that, if you're asked about the homogeneity of the variances, not super useful because you'd have to run an SPSS first. The other way, other method that's easier by hand is something called an F-max test. Okay. So F-max basically says you want the ratio of the larger variance over the smaller variance. Right? That ratio should be less than or equal to 10. Now, in some books and even some places in my own materials that I've tried to sort of get rid of, but somehow it keeps coming back. Part of this too is you might be thinking like, how hasn't this guy like figured out how to get rid of this stuff? So what happens sometimes is I'll go through and fix things. This has happened with lectures. This happened with all kinds of stuff. Go through and fix things, and then in a next semester, or next year, when the class, like a Canvas class, gets repopulated, it'll pull materials over. It sometimes pulls over the old material and not the new stuff, and then we're back to sometimes the same weird things keep popping up. So F-max, some places it'll refer to less than or equal to 3. If you use 3, you're gonna come into problems all the time. You're gonna run into violating F-max too often. And in many places, more places than I've seen it with 3, I've seen 10 used a lot more. 10 is what I use when I teach the 485 US class. 10 is what I use when I teach 524 and 534 and other places. So to keep everything consistent, 10 is sort of the magic number. Which tells you right there that homogeneity variance isn't a super strict idea, because it's just telling you that the ratio of variances, you don't want one variance to be more than 10 times the other variance, which obviously I can tell here without doing anything, because these two are identical. But if you're asked about homogeneity and you need to know sort of what to do, well, there's an easy sort of by hand thing, which is just take the larger variance. In this case, it would be 2.786. Not the variance of the larger group, mind you, but the numerically larger variance, and divide it by the smaller variance. If that ratio is less than or equal to 10, then you're good. Then the variances are homogeneous. If it's over 10, greater than 10, then there's a problem. It means you're into this heterogeneity of variance realm, and you really shouldn't pool variances and do all this stuff. It becomes problematic because you're averaging or pulling together things that aren't the same. They're not even similar, so why are you averaging them? Anyway, so that's sort of a side, digression. It's related to this, but it's not directly, addressing the 6 steps. It is in the sense of, to be able to do this step, you really need to be able to assume the homogeneity of variance stuff. So it should be part of the steps. But if you notice that these variances are remarkably different, you probably should test them before you pull them together. Or if you're asked to do it as part of a exam or practice problem or something like that, you should then use an F-max to figure it out. All right, so we figured out a pool variance, 2.745. Great, that's step 1. In the last slide, we figured out the pool variance is 2.745. So now that we know that, we can insert it into this equation, where we're going to substitute the pool variance in for sigma squared that we saw earlier. I'm going to put it in the same number. I'm going to put it in twice. So this is 2.745. This is also 2.745. I just have 2 different n's. The first n for group 1 was 8. The n for group 2 was 10. Like that. So I need to take 2.745 divided by 8. 2.745 divided by 8 equals, so this is 0.343. 2.745 divided by 10 is obviously 0.2745 or 0.278. This is 0.278. All right, so I need to add those together. 0.343 plus 0.278 equals 0.621. So if I add them together, this is 0.621 621, still square rooted. And if I take the square root of that, 0.621 square root is 0.788. Okay, 0.788 then is my standard error of the difference between the two means. So I've now covered step 6a, step 6b by getting these two, by calculating the standard error. I can now then complete step 6 by plugging that in. So the two means were 10.25 here, 10.25 minus 8.4, right, over 0.788. All right. So I can do that. 10.25. Oops. 10.25 minus 8.4 equals 1.85. So this equals 1.85 over 0.788. So 1.85 divided by 0.788 equals 2.348. 2.348 is now my T observed. Okay, 2.348. So again, there's a couple steps in here, right? So it's not as straightforward as one sample or dependent samples where we can just go directly just to calculating the standard error. We got to do a couple things. We got to figure out the pooled variance first, and we should really be testing whether or not we can do that by the F-max test or something. But as part of that, if we decide we can pull them together, we should pull them together, and then we plug in the pooled values for sigma, and that will give us a standard error, the difference between the two means based on S. We can plug that into T and get a T observed. And now what? So that's step 6. We figured out T observed. Now we need to compare our T observed, our observed value here, to our decision rule, and then make our decision. Since, okay, so I need this is my T observed value, since 2.348, that's the number we got down there. We also need that here, 2.348. Okay. So again, just to reiterate, these two, it's a huge or here. You can do one or the other, but just again to be complete, we need to go through the whole thing. So we found our T observed, and we previously found our T criticals. So let's go look at those real quick. All right, remember the one tail is 1.746, two tail is 2.12, so we can go back and plug those in. So two-tailed test, this is 2.12. For the one-tailed test, this is 1.746. Let's check on those just to make sure I didn't remember them wrong or flip them or something. 1.746, 2.12. Awesome. If you had found these using the T table, they'd be, to 3 decimals or something, or to 4 decimals, but they'd be the same idea. Since 3.48, which is our T observed value, is larger than 2.12, we would reject the null hypothesis using a two-tailed test. Since 2.348 is larger than 1.746, we would also, or instead of, reject the null hypothesis under a one-tailed test. So either way, right, because this is, with the two-tailed test, because this is positive, right, remember we were interested in the absolute value, but because 2.348 is larger than the positive 2.12, it tells me that, right, that here I have 2.12, and I have negative 2.12 as part of my two-tailed test. It tells me that it's here, right? It tells me it's larger than 2.12, which means that there were more aggressive behaviors for GTA than for Lego, because that's how we subtracted them. So that means either way, there is evidence that the violent video game, the Grand Theft Auto, increased aggressive behaviors. Okay, so this is a significant difference. There's some evidence to support that the amount of aggressive behaviors after gameplay was higher for Grand Theft Auto than it was for the Lego City Undercover. Okay, and that's all 7 steps. Step 6 here is a little bit more complicated than it has been in the one sample dependent samples, but it's not huge. Calculate this, the pool variance, plug the pool variance into the standard error equation, and use that to calculate t. So there's a couple extra steps in there. Other than that, not too bad. So, like I mentioned before, what if you have heterogeneous variances, right? What if you go to do an Fmax test? What if you go to do that and the variances are just dramatically different? So this refers to the case of unequal population variances, where the variances are so different it doesn't make any sense to pool. So when that happens, we don't pool the sample variances, we simply add them together. So if you have a variance of group 1 and a variance of group 2, and you decide that, you do an Fmax, say, and when you take the ratio, the variance of 2 over the variance of 1 is larger than 10, okay? We find it's bigger than 10. We're just going to add the 2 variances together. We're not going to pool them, we're just going to add them, okay? And then we adjust the degrees of freedom and look T up in the tables for the adjusted degrees of freedom. So how do we adjust? Well, instead of taking n1 plus n2 minus 2, right, we don't do that. Whichever n is smaller, minus 1. And that's going to be our new degree of freedom. So because the variances are not equal, we're going to do some corrections. We're going to, instead of sort of pooling, we're going to add them together, which is already going to make the standard error huge. And it's going to make it much bigger. So our standard error is going to be bigger. So it's going to make t smaller. So we're sort of almost like handicapping the test so that we're going to use a larger standard error. And we're also going to use a smaller degree of freedom. Smaller degrees of freedom, if we go back to our t table for a second, just to remind us, as the degrees of freedom get smaller, right, the critical values get bigger. So we're going to use a larger critical value and a larger standard error, which means a smaller t observed, at the same time. And if we still find a significant difference, if we still find the groups are significantly different from one another, then we can feel fairly confident that a significant difference is there despite violating the sort of homogeneity of variance assumption. So we're assuming homogeneous variances, but when they're not, we're going to set ourselves up to have a much harder test, a much more challenging, difficult test to surpass. Our t observed is going to be smaller than it should be, or than it normally would be, because we have a bigger standard error. Our critical value is going to be larger than it should be because we're using a smaller degrees of freedom. And if under that circumstance we're still able to find a significant difference, then we can feel fairly confident that it exists despite the flaw in not having variances that are somewhat equal or homogeneous. So let's talk about effect size. We talked about effect size when we were looking at the one sample dependent samples test. And again, to reiterate here, the reason we talk about significance testing and effect size separately is they're asking 2 different questions. The significance testing really is looking at, is the difference we found likely to have occurred by chance? Is it due to random variability across samples, or is there potentially a real difference between our sample and the population, or for the different scores between the 2 samples, or in this case between the 2 independent samples we have? But it doesn't tell us about whether the difference is large, whether or not it's something that is remarkable, right? And oftentimes people get that confused with significance. So here, the effect size tells us, all right, well, if I know that the difference between the 2 groups is roughly 1.85 aggressive behavior, whatever the hell that means. So it's not quite 2 aggressive behaviors, but Again, that's the sort of raw effect. There was 8.25 for the Grand Theft Auto, 10.25 for Grand Theft Auto, and then 8.4 for the Lego City Undercover. All right, but is that a lot? I don't know. So the most common way to go about doing effect size is to create a standardized effect size using Cohen's d again, which is this idea of using the difference divided by standard deviation instead of standard error. The standard deviation to see how many standard deviation units are the groups apart. The problem is we have two. We have standard deviation for Grand Theft Auto, standard deviation for the Lego game. And when we did a dependent samples test, we're like, okay, well, we have two. We have the variance of the differences. We have the variance for the standard deviation for the pre-test. We have the standard deviation of post-test, and we have standard deviation for the difference. Which one of those do we use? We decided, well, we're going to use the pre-test, right? Which may have surprised you. We're going to use the pre-test because the pre-test was sort of unadulterated by the intervention, whatever we did to them. So here, we're going to take a different route. Instead of picking one or the other, since we already have a pooled variance, that 2.745, we already have a pooled variance, we can take the square root of the pooled variance and get a pooled standard deviation. So we're going to use the idea that these two samples are coming from the same population, or at least estimating the same value in population, and use that information we've already found, the pooled variance, to take the square root and find a pooled standard deviation. So if I take the square root of our pooled variance from earlier, 2.745, I get to the pooled standard deviation is 1.657, and I want to use that number as the denominator for my Cohen's d effect size. All right, so let's look at this. We have that d equals to, this really, again, if I'm going to be consistent with what I said before, this really is not Cohen's d, but this is like the measure of d hat. This is the estimated population effect size, right? Because we're using all sample values. So we have our two means, mean for group 1, mean for group 2. I'm going to subtract them, and we'll divide by that pooled standard deviation. All right, so I got it all plugged in here. 10.25 minus 8.4, we said was that 1.85 or whatever number, divided by our pooled standard deviation. All right, so our difference is only 1.85, or is 1.85, almost 2 units. Our pooled standard deviation is 1.657, which is smaller. So what this tells me is that the differences in effects, or in aggression, the differences in aggression as measured by effect size is over 1 standard deviation different, right? So we got 1.12 standard deviations apart. So whatever's going on, if playing the violent video game, playing Grand Theft Auto, is actually affecting aggression, not only is it affecting aggression in a way that's significant, it's not due to chance, it's actually moving people's aggression 1.12 standard deviations apart from those who are playing the Lego City Undercover. Just to remind ourselves for Cohen's d2, remember 0.2 is small, right? 0.5 is sort of medium, moderate. 0.8 is large, and there isn't anything above large, but this, this 1.12 effect is, past 0.8, so we're into a large effect size. So not only is playing Grand Theft Auto versus playing Lego a significant, right, not likely to occur by chance alone effect, it's also a fairly large one. So it's a large, significant effect. All right. 1.12 standard deviations apart. It's quite big. So just like with the one sample test and the dependent samples test, we can calculate confidence intervals. So again, if you were to do this multiple times, this will give you an idea of the range of differences you can expect your samples to have. Right? Knowing we know about the standard error that we figured out, we know the standard error of the distribution of the differences between two means, we can use that and a two-tailed critical value to give ourselves what that would look like. What are the 95% of that distribution, what would I expect the differences between these means to look like? I can actually compute that using this. So I'm going to take my two means, I'm going to subtract them. So I know this already is 10.25 minus, this is 8.4. All right, so I have that in there. So now I need the two-tailed. Now remember, I want a confidence interval to be equally above and below my estimated difference. So that's why it's got to be two-tailed, not one-tailed. If it's one-tailed, it's sort of lopsided. I want it to be two-tailed, so I need the two-tailed value, which from before, a couple slides ago, our two-tailed value was 2.12 or 2.1199. So this is the 2.12 is my two-tailed t value that I had from when I was doing a two-tailed version. So I know that already. And I know that this is 0.788. It's our standard error that we had calculated from a couple slides ago. So I have those numbers. I can just plug them in. 2.12, 0.788. So if I multiply those together, 2.12 times 0.788 equals 1.671. So 1.671 is the number we're going to be adding and subtracting. The difference here is at 1.85. So 1.85 is the difference, plus and minus 1.671. So 1.85 minus 1.671 equals 0.179. So on the low end of my confidence intervals is 0.179, which is less than the difference between the two means, the two population means I'm trying to estimate, which I think this should be less than or equal to. So this is less than or equal to. All right. Then I need then the top end, which is 1.85 plus 1.671, which is 3.521. So my 95% confidence interval around the difference between our two means is that 0.179 is less than or equal to the difference between the populations I'm trying to estimate, which is less than or equal to 3.521. So the real populations that our samples are coming from fall between these numbers. It also tells me if I was to do this experiment, this study 100 times, okay, I would expect to find values in this range 95 of those out of those 100 times, and then 5% of the time I'd find values that are outside of this range. All right, so this is what the 95% confidence interval tells us. It uses our sample value to estimate what are the likely populations our samples could have come from, and it gives us a range of those values. The probability is 0.95 that based on the sample values, the interval formed in this way includes the true value of the population difference that we're trying to estimate. It is this probability that the interval includes that number given our sample differences. And like I started to say before, given our interval at 0.719 to the 3 point whatever it was, does 0 fall in the interval? Well, 0 is not in that range, which means that it sort of matches our significance testing. So here's the idea. Significance testing says, given a population of 0, what's the likelihood of getting this sample? Well, we decided it was less than 5%, which is why we rejected the null. This is doing the same thing, but in reverse. This is saying, all right, given our sample difference of 1.85 or whatever, what are the likely populations that this sample could have come from? And because 0 doesn't fall in there, it means that a population where the means are the same, have a 0 difference, is not a likely parent population for our samples. So it's really saying the same thing, but just in reverse. One's from the perspective of the population. Given this population, is this sample likely? And we said, well, no. That's why we rejected the hypothesis. This is coming from the perspective of the sample. Given our sample difference, what are the likely populations? And we said, well, they're 0.719 or whatever, the 3 point whatever, those numbers. And because 0 doesn't fall in that interval, a population where the mean differences are 0 is not a likely parent population for a sample, which is really leading us to the same conclusion we did when we did the hypothesis test. Given this population, this sample seems odd, that's why we reject. Given this sample, here are the populations. A population of 0 doesn't seem to fit, so they both sort of match one another, which is nice. There's a nice symmetry there. There's some match between them. That doesn't always happen. Sometimes you'll reject with one, the other one will say something different, because sometimes you're using a one-tailed test to do your significance test and switching to a two-tailed test for the confidence interval, and you may get different answers. But lots of times it will sort of match up, unless your t-observed value is super close to your critical value. Otherwise, it likely will match up pretty well. All right, so that wraps up independent samples tests. So we covered one sample, dependent samples, and independent samples tests, which then sort of brings us to the end of sort of looking at just two samples at a time. As we move forward from here, our next topic is going to be talking about analysis of variance, which takes this idea of comparing two groups and expands it. Okay, well, how do we know if three groups are different, or four, or five, or more groups? How do we take a look at differences between groups that are more than just two? So we can have 3 independent, 4 independent groups. How do we actually look at that? Because t-test will start to fall apart somewhat and add some issues if you just do multiple t-tests. So that's going to be the next big topic, is analysis of variance going from here. And that's it for independent samples tests.